students, welcome to Sunil's tutorial. I'm Sunil Midwani and today we'll be doing this chapter called as Kinetic Theory of Gases. Let's see what do we mean by molar specific heat at constant volume. Now, molar specific heat at constant volume. Okay, we've already done molar specific heat at constant volume. Let's see what is the last thing that we've done. We've done
constant
pressure also, we've finished. Right? Next, let's see the dimensions of specific heat. Now, specific heat we said is nothing but specific heat C is equal to heat upon m theta. Therefore, dimensions of specific heat will be dimensions of heat upon dimensions of m theta. Now, dimensions of heat are m1 L2 T minus 2 upon m1 theta 1. So in that case, the dimensions of specific heat will be nothing but m0 L2 T minus 2 theta minus 1. Those are going to be your dimensions of specific heat. Next, let's try to find a relationship between Cp and Cv, molar specific heat at constant pressure and molar specific heat at constant volume. Let us consider a cylinder fitted with a weightless, frictionless piston. Right? Let's assume that V is the volume of the gas inside the cylinder. Right? Now, so let us consider 1 mole of gas enclosed. Let's consider 1 mole of gas enclosed in a cylinder provided with airtight piston. Right? Now let's assume that P, V and T are the pressure, volume and absolute temperature of the gas in the cylinder. Let P, V and T be the pressure, volume and absolute temperature of gas in cylinder. Right? Now, let us assume case 1. Let us heat the gas keeping the piston in fixed position. Heat the gas. Let the gas be heated. Keeping the piston fixed. Right? Now, if the piston is kept fixed, that means the volume does not change. If the piston is kept fixed, so that the volume of the gas does not change. Right? Now, in this case, the entire heat supplied to the gas is used to increase the temperature. Since the volume is not changing, I can say hence the entire heat supplied to the gas, is used to increase the temperature of the gas. Right? Now let us assume that dT be the rise in the temperature. Let dt be the rise in temperature. If dt is the rise in temperature, then I can say that the quantity of heat absorbed is going to be mass into specific heat into rise in temperature. Right? Heat absorbed H is equal to mass. I have taken 1 mole of gas. Specific heat, since I am keeping the volume constant, this is CV into rise in temperature, we said is dt, right? Where CV we know is molar specific heat at constant volume. CV is molar specific heat at constant volume. Now let's do the experiment again, right? Now, let the gas be heated at constant pressure. Let the gas be heated at constant pressure. Let's assume that the gas is heated to constant pressure such that the temperature rises to T plus dt. T was the initial temperature, it rises to T plus dt. Now in this case, since the volume is not constant, that means some external work has been done, right? I can say since the volume of the gas does not remain constant, hence it expands and performs external work. Right? Now, therefore the piston is going to be pushed in upward direction. Therefore, the piston is pushed in upward direction. Now, once I know that the piston is pushed in upward direction, that means some part of the heat energy is used to perform external work, and the remaining part of the heat energy has been used to increase the temperature, right? So if the piston has moved up, I can say therefore some part of the heat energy is used to perform external work, and the remaining part is used to increase the temperature of the gas, right? In this case, I can say that the heat absorbed is nothing but mCT, mass into specific heat at constant pressure, because I am keeping the pressure constant here, into the change in temperature, that is dT, where Cp stands for molar specific heat at constant pressure. Molar specific heat at constant pressure. Now, I can therefore say that the heat Cp into dt consists of two parts. This heat absorbed consists of two parts. One, the heat required to raise the temperature. Heat required to raise temperature. This particular heat is used to raise the temperature. Consists of two parts. Heat required to raise the temperature without external work. And the second part of this heat is used to perform external work. Heat required to perform external work. But heat required to raise the temperature without external work is heat required to raise temperature without external work is nothing but CV dt. Thus, I can therefore say that Cp dt is equal to Cv dt, that is the total heat energy is used to raise the temperature plus external work done dW, right? Now let us assume that A be the area of the cross section of the cylinder. Area of cross section of cylinder, right? And dx is the displacement. Dx is the displacement of the piston. Displacement of piston, right? In which case I can therefore say that the work done during the expansion is nothing but work is force into displacement, right? Force is going to be nothing but pressure into area into displacement, that is P into A into displacement, that is dx. But area into displacement, area into length is volume, but area into length is nothing but volume, and this is dW, that is the increase in volume during the expansion. Increase in volume due to expansion. Therefore, the work done is P dV, right? Hence, I can therefore say that you could say that in terms of units of heat, I can say dW is P dV upon J. So you will get it in terms of calories, where J is the mechanical equivalent of heat, where J is mechanical equivalent of heat, right? Now, if I substitute this in my original equation, I'll get therefore Cp dt is equal to Cv dt plus P dV upon J, right? So in which case this I can say, but by Gass's law, PV is equal to RT for 1 mole. For 1 mole of a gas, PV is equal to RT. So in that case, let us assume that if the volume increases by dV, the temperature will increase by dt. Let volume increase by dV when temperature increases by dt. So that means I'll get PV plus dV, that will be the new volume, is R T plus dt. So you will get PV plus P dV is RT plus R dt, right? Now, PV we said is nothing but RT plus PdV is RT plus RDT, RT gone, so I'll get PdV is RDT, right? So I can substitute this, therefore I'll get Cp dt is equal to Cv dt plus PdV can be written as RDT upon J, right? Therefore I could say that divide by dt. If I divide by dt, I'll get Cp is equal to Cv plus R upon J. Therefore, Cp minus Cv is R upon J. That is the relationship between Cp and Cv.
So how do you get RT on the LHS?
Yes.
So, yes, sir, above that. Yes, so that's
Yes.
RT.
What's the value of PV? The value of PV is RT. I'm substituting the value of PV as RT, right? And then the RT on either side will get cancelled, right? This particular relationship is called as Mayer's relationship. This relationship Mayer's relation, right? That, but let's assume that M represents the mass of 1 mole of gas. Let us assume that M, capital M, is mass of 1 mole of gas. If capital M is mass of 1 mole of gas, then I can say that the principal specific heat small Cp is nothing but Cp divided by M. Similarly, small Cv so therefore small Cv will be capital Cv divided by M. Now if I substitute this in Mayer's relationship, I will get Mayer's relationship says that Cp minus Cv is equal to R upon J divided by M. If I divide by M, I'll get Cp upon M minus Cv upon M is R upon Mj, but Cp upon M is small Cp minus small Cv is R upon Mj. This is how you represent this in terms of principal specific heat. Fine, do we get this thing clear? So do we understand Mayer's relationship, or this is also called as the relationship between Cp and Cv, right? Okay, we'll stop this here for the day. Thank you very much.